What specific problem does your work aim to solve, and how does it relate to the understanding of representational dynamics during overtraining in neural networks?
My work aims to solve the problem of understanding how representations in the mouse piriform cortex evolve during overtraining on a binary odor discrimination task, particularly after achieving ceiling performance. We observe that, despite no visible changes in behavior, the decoding accuracy of training labels from population activity increases throughout overtraining, indicating continued representational learning. This phenomenon is analogous to the grokking observed in deep learning, where networks continue to learn and generalize long after training accuracy has plateaued. By analyzing neural firing rate data, we find that the separation of target and non-target odor representations increases during overtraining, suggesting that the underlying representational dynamics involve margin maximization, similar to the behavior of deep neural networks. Our findings contribute to a deeper understanding of how neural representations can continue to evolve and improve generalization capabilities, even after apparent mastery of a task.
Can you explain how the proposed method works? Illustrate it step by step, detailing the mathematical definitions such as margin, feature representation, and the SVM classifier during overtraining.
The proposed method investigates the dynamics of odor representation learning in the mouse piriform cortex during overtraining on a binary odor discrimination task. First, the method defines the feature representation phi_tx as the neural response at time t for a given input x. The margin mt of a maximum margin classifier, specifically a support vector machine SVM, is then defined as the distance from the decision boundary to the nearest data points, which evolves over time as the feature representation improves. During overtraining, the margin increases, indicating that points close to the decision boundary, which may have been misclassified initially, become correctly classified as the representations separate further. The method tracks the average distance to the closest 1% of points. Finding that this distance increases significantly during overtraining, suggesting that the neural representations are actively learning to maximize the margin, akin to the grokking phenomenon observed in deep learning. This process illustrates how continued learning occurs in the cortex, leading to improved generalization on unseen test examples.
Could you provide a simple yet illustrative example demonstrating the inner workings of your proposed model, particularly regarding the concept of margin maximization during overtraining?
In our study, we illustrate margin maximization during overtraining using a synthetic model of the odor discrimination task. Initially, the model is trained to classify a target odor from 200 non-target odors, achieving a low training loss. However, during the overtraining phase, we observe that the margin, the distance from the decision boundary to the nearest data points, increases significantly. For example, as the model continues to train, the closest 1% of points to the decision boundary become more accurately classified, indicating that the representations of target and non-target odors are evolving to enhance the classifier's robustness. This process mirrors the grokking phenomenon observed in deep learning, where the model's performance on unseen test examples improves due to the maximization of the margin, even when training accuracy has plateaued. Thus, our model demonstrates that continued learning during overtraining leads to better generalization on difficult, held-out examples by refining the decision boundary through margin maximization.
What are the theoretical or practical benefits of using your approach compared to existing methods for studying overtraining and representation learning in both neuroscience and machine learning?
Our approach offers several theoretical and practical benefits for studying overtraining and representation learning. Firstly, we provide a biologically faithful synthetic model of the piriform cortex that captures the dynamics of continued learning during overtraining, demonstrating how representations of target and non-target odors actively separate despite no behavioral changes. This aligns with the grokking phenomenon observed in deep learning, where late-time feature learning leads to improved generalization. Secondly, our findings suggest that margin maximization serves as a key mechanism, driving representational changes, offering a geometric perspective that enhances understanding of how neural networks and biological systems can achieve robust classification. Additionally, we propose a novel explanation for the overtraining reversal effect, linking it to improved task model alignment and feature learning, which has implications for both experimental psychology and computational neuroscience. Overall, our work bridges insights from machine learning and neuroscience, providing a comprehensive framework for understanding representational dynamics during overtraining.
How is your method validated? Please discuss the experimental design, the datasets used, the metrics for performance, and how these validate the effectiveness of your findings.
Our method is validated through a comprehensive experimental design involving adult mice trained on a binary odor discrimination task, where they learned to distinguish a target odor from numerous non-target odors. The dataset consists of neural firing rate data collected from the posterior piriform cortex during an overtraining period of 18 days, following an initial training phase where the mice reached ceiling behavioral performance. We assess performance using metrics such as decoding accuracy of training labels from population activity and the margin of a maximum margin classifier, which increases throughout the overtraining period, indicating improved separation of target and non-target odor representations. Additionally, we analyze representational similarity matrices and track the average distance from the classifier to the closest data points, which further supports our findings of continued representation learning despite unchanged behavior. This validation demonstrates that the observed neural dynamics align with the Grokking phenomenon in deep learning, reinforcing the effectiveness of our model in explaining the representational changes during overtraining.
What specific results did you achieve with this method, particularly in terms of decoding accuracy, and the implications of these results on understanding the overtraining phenomenon?
We achieved significant results in decoding accuracy during the overtraining phase, where we observed that the decoding accuracy of training labels from population activity increased throughout overtraining, despite no visible changes in behavior. Specifically, we found that the margin of the maximum margin classifier increased over the course of overtraining, indicating that previously misclassified odor trials became correctly classified as the representations of target and non-target odors continued to separate. This suggests that even after reaching ceiling performance, the neural representations in the mouse piriform cortex were still evolving, which aligns with the hidden progress phenomenon observed in deep learning. Furthermore, our findings imply that this continued representation learning may enhance generalization on unseen odors, as evidenced by improved performance on held-out test examples after the overtraining period. Overall, these results provide a deeper understanding of the overtraining phenomenon, highlighting that learning dynamics can persist beyond behavioral mastery, akin to the Grokking phenomenon in deep neural networks.
What are the limitations or drawbacks of your method, especially concerning the generalizability of your findings to other tasks or neural systems?
The limitations of our method primarily stem from the observational nature of our neural data reanalysis, which restricts our ability to make definitive claims about the representational dynamics during overtraining across different tasks or neural systems. Specifically, we cannot ascertain whether the cortical representations begin in a lazy or rich regime, as the absence of test data during the training period limits our understanding of initial learning dynamics. Additionally, while our synthetic model captures the behavior and neural correlates of the mouse olfactory system, it may not fully generalize to other neural systems or tasks due to the unique biological constraints and mechanisms at play in the piriform cortex. Furthermore, the proposed biological drivers of late-time learning, such as energetic constraints or implicit penalties on uncertainty, remain speculative and require further empirical validation to establish their relevance across different contexts. Lastly, our findings regarding the overtraining reversal effect are specific to the odor discrimination task and may not extend to other types of learning or cognitive tasks without additional evidence.
What future work do you suggest based on your findings, and how could these suggestions enhance the understanding of representational dynamics in the brain or improve your proposed model's applicability?
Based on our findings, future work should focus on directly testing our hypotheses regarding representational dynamics during overtraining in the mouse piriform cortex. This could involve designing experiments that manipulate the overtraining duration and observing the resulting changes in neural representations and behavior, particularly in relation to the margin maximization we propose. Additionally, exploring the biological mechanisms that drive late-time learning, such as energetic constraints or unsupervised penalties on uncertainty, could provide deeper insights into the underlying processes in the brain. Furthermore, extending our synthetic model to include more complex tasks or different sensory modalities could enhance its applicability and help validate our theoretical predictions about feature learning and task reversal. Such investigations would not only clarify the dynamics of learning in the cortex, but also bridge the gap between computational models and biological learning systems.